Now that we know what prime numbers are, let's ask a computational question. So how can we systematically list all prime numbers up to some given integer n? So one possible method, of course, is the naive approach. You just check each number at a time and test whether it's divisible by smaller numbers, and then you go and do that a lot. And this works, but it can be very slow if n is large, right? It'll take a long time. And so the question is, are there better methods? And the answer is yes. I mean, there are many of them, but we're going to talk about a simple one, and it's actually a very classical one called the sieve of Eratosthenes. So the sieve of Eratosthenes is an efficient ancient method to do this. And the idea is quite simple, and here we have the instructions, but I think it's easier to look at it with an example. So let's say here you want to find all the prime numbers up to 100. So what you do is you list up all your numbers from 1 to 100. Now, of course, you'll remove the number 1 because it's not prime. And then what you do is you start with the next number. So you start here with the number 2, and then you go and you cross out, and so here we just put them in light gray, you cross out all the multiples of 2, okay? So now these numbers are definitely not prime because they are all divisible by 2, right? Then you go to the next number that you haven't eliminated yet, and you do the same thing. So now you remove all the multiples of 3. And if you do that, this is what will happen. Okay. Now you go to the next number that you haven't removed. So for example, you removed 4 because of the 2 here. So you go to the 5. And now you remove all the multiples of 5. So 10 you remove, 15, and you go on and remove all multiples of 5. So now that we've removed multiples of 2, 3, 5, and 7, since the square root of 100 is equal to 10, which is another way of saying that 10 squared is equal to 100, we don't need to check beyond that, right? We only need to check the primes that are up to 10. The reason for that is that if there is a number after 10 that you multiply by something to get 100, it needs to be multiplied by a number smaller than 10. Because if you multiply two numbers larger than 10, they both have to be, like, if they're both larger than 10, then when you multiply them together, it's going to be more than 10 times 10, which is 100. So you don't need to remove, like, you don't need to do this procedure beyond the square root of the number that you're interested in. And so that's it. So if you list out all the numbers that are multiples of 2, 3, 5, and 7, and you remove them, you're done. So all of these are your prime numbers here. So 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. So all of these, so these are all the prime numbers that are smaller than 100. Okay. Now that we have a list or a way to list the prime numbers, we can ask a different question, right? We can ask, so how many primes are there up to a large number, n? For example, how many primes are there less than 1,000 or less than 1,000,000, right? And so the sieve can, of course, answer for specific n, but sometimes we would like to have some type of result. How does this grow with time, or like what happens with time? And this actually leads to one of the most important theorems in number theory, which is called the prime number theorem. So what is the prime number theorem? So the prime number theorem says the following. If you denote by pi of n, so this function here for every n, this is going to be the number of primes that are less or equal to n. So this is just counting. So pi of 1,000,000 is how many prime numbers are there less than 1,000,000. And what the prime number theorem says is that this is approximately n over log n. So, and that it's like a good approximation. And so another way to say this is that the probability that a random chosen integer between 1 and n is prime. So if you have this amount of primes up to n, and you have n numbers, when you divide by n, the probability that if you choose a number between 1 and n at uniform, the probability that it will be a prime number will be 1 over log n. And so of course log n grows, but it grows very, very, very slowly. So what's happening here is that, but it does grow and diverge. So what's happening here is that primes become less common as the numbers get larger. So for example, for numbers with like 1,000 digits, you have around 2,300 roughly, so very roughly it's like 2,300 such numbers are prime. For numbers with like 2,000 digits, roughly 4,600. And so the idea is simple. The primes never run out, but they become rarer and rarer, right? And this sort of tells you the way in which that happens. And so this is a nice theorem, and I'll finish it off showing two interesting open problems that are quite old and very famous. So these are conjectures, so that means they haven't been proven. These are things that for one reason or another maybe we believe to be true, but we haven't proven that they are true or shown that they are false. And so the first is Goldbach's conjecture, and it's from 1742, so quite a while. And it says that every even integer greater than 2 can be written as the sum of two prime numbers. So for example, the number 4, you can write it as 2 plus 2, right? The number 10, you can write it also as the sum of two prime numbers. 28, 100, and so on. And so this has been checked computationally for extremely large numbers, but no one has done like a full proof. In principle, maybe there exists some very large integer that cannot be some very large even integer that cannot be written as a sum of two prime numbers. We don't know, but we haven't found one. And so this is an open problem. And it shows how many statements that can be quite simple to understand, they seem to be very hard to be able to prove, right? And shows how, in some sense, how little we know about maybe fundamental stuff or basic stuff in some way. And then there's the twin prime conjecture. So this is another famous open problem from 1849. And so twin primes are pairs of primes that differ by 2. So for example, 3 and 5 are prime numbers, and the difference between them is 2. So this is a twin prime. 5 and 7, 11 and 13, and so on. And so the twin prime conjecture says that there are infinitely many such pairs. So we know that there are infinitely many primes, but this conjecture is saying like something more specific. It's saying that having these primes that have a gap of 2 between them keeps appearing forever, right? And so like the Goldbach conjecture, it's also open, right? We've checked it computationally for very large numbers, and it seems to go. It seems that you're always able to find, but again, it's an open problem.